We are on page 136, Lewis structures for ionic compounds. So yesterday we spent our time looking at Lewis structures. Electron dot configurations is the other name you may hear at times. But looking at Lewis structures, and what is the significance of a Lewis structure? What does it show us? Correct. The number of valence electrons for that element in its current state. How many valence electrons does that particular atom have? And by looking at the valence electrons, what are we determining? Or what can we eventually determine? What's the most significant thing that's impacted by the number of valence electrons? It's kind of a general concept, not a specific thing, but how it reacts chemically, right? I said yesterday, how an atom reacts chemically is dictated by the number of valence electrons that it has. So the fact that an element or a particular atom that we're looking at has 7 protons or 8 protons or 9 protons, that's significant to the degree that it needs to have the same number of electrons to be a neutral atom, right? 8 protons means it needs to have 8 electrons. 8 positive charges counterbalanced by 8 negative charges so that it overall has a 0 charge. But we start talking about how things react chemically, it's significant that it has 8 electrons or 7 electrons in its valence shell. The reason that it has that many is initially for the neutral atom is because it has a certain number of protons. And we covered that again in the last module. So yesterday we talked about Lewis structures, showing how many valence electrons that an atom has. And we also discussed this idea of the octet rule. Real quickly, what does the octet rule say? Close. Close. We'll said that the octet rule says that all atoms want to achieve 8 valence electrons. Okay? Most. The octet rule says most or virtually all. There are 4 exceptions. Hydrogen, helium, lithium, and beryllium. The first 4 elements. They're exceptions because their octet rule drives them to have how many valence electrons? Not 8, 2, right? 2. Now think about it. Why only 2 for those 4 elements? If they only have 2 electrons, what have they just filled? The 1s orbital. The 1s orbital is full when they have 2 electrons. Hydrogen has a 1s 1 electron. To fill the 1s orbital, it needs a second electron. Once that second electron's there, the orbital is full. Lithium has a 1s 1 and 1s 2 and also has a 2s 1 electron. Now it could fight to get more. It could fight to try to get 5 more electrons to have 8 total. But actually it's at the second energy level, so it'd have to fight to get 7 more electrons to fill the second energy level. Or it can lose 1 and fall back to a complete 1s orbital for 2 electrons in that orbital. So for the first 4, hydrogen, helium, lithium, and beryllium, their octet rule says they're going to be fulfilled when they have 2 electrons. For everything else, they're looking for 8 in their valence electrons, their orbitals, the highest energy level. Now, when we did the electron configurations, we got into the Ds and the Fs, not so much the Fs, but the Ds. But remember, whenever we finally started filling electrons and started filling in the D orbitals, what was significant about their energy level? It was what compared to the S or whatever? Like say we're in the 4th energy level, 4s1, 4s2. This D level is what energy level? Right, it's 1 less, so it's the 3rd energy level. So even though technically the 3D1 would fill after the 4s2, it's a lower energy level, so it's not part of the valence. Okay? So Ds and Fs, they're not going to be part of your valence. Your valence is going to be basically at that energy level, how many S and P electrons do you have? That's going to be the key. That's why you're not going to see many problems, especially in this module. We will get some. But for right now, we're not going to consider molecules that are made up with D orbitals because they act weird. They don't follow the nice basic high school first chance chemistry rules that we need. So we're going to make some generalizations. Just like we said, everything to the left of the stair step is a non-metal, or excuse me, is a metal, and everything to the right of the stair step is a metal. They've got those transitionals and those metalloids and things that act weird. We kind of try to wash out as much of the weird stuff as possible so you get the basic concepts down. Okay? So there's going to be times when I say, you know what, don't worry about that. And if you're really inquisitive mind, you're going to go, but I really, really care. Like, I appreciate that. Let's talk after class, because for the purposes of this class, if we dive into that, it's really cool stuff, but it's absolutely a sidetrack for everybody else, and it can become confusing. That's why today we're going to talk about some rules that are generalized. And for the purposes of this course, we're going to treat them as if that's the absolute fact. Knowing that later on we do different kinds of chemistry, higher level chemistry, there seems to always be some little nuance of a special case rule that throws a lot of things off from the basic understanding. We're just dealing with basic understanding here. So, yesterday, we started drawing Lewis structures for individual atoms. And today we're going to start using sodium chloride as an example of how an ionic molecule is formed. We're going to start with ionics because ionics are the easier one. Easier than the covalents. We've already done the naming paradigms, right? Ionic compounds and covalent compounds. And we said ionic compounds, when they're formed, they're only formed in one way. There's only one way that an ionic bond can be formed. And so it has a very simple name. It has the metal name and then the non-metal name with the "ide" ending. We said covalent molecules, however, they get a little more complicated because they can combine in multiple ways using the same different elements. So carbons and oxygens, it could be a CO, it could be a CO2, multiple combinations with the same elements. Today, we're going to start to learn why that is. And we're going to start by looking at the ionics. We're going to start with a basic example from the book, sodium chloride. Hopefully you'd agree that to have sodium chloride, we have to have a molecule, or excuse me, an atom of sodium and an atom of chlorine. We're going to start by, first of all, when we do this, we're going to say, is this a ionic or covalent molecule that's going to be formed by these two different elements? Ionic, right? Because you see, I have a metal and I have a non-metal. And I'm not sure yet why that is, but I've been told when I have a metal and a non-metal, it forms an ionic bond. Let's show why that is by, first of all, drawing the Lewis structures for both of these. What's my Lewis structure for sodium going to look like? Good. We're going to have one electron, right? One valence electron. How do I know? Looking at the periodic table, sodium is in the first column. I know that whatever its configuration is, it has, because it's sodium, it has 11. It also has a 3s1 electron. That's its highest energy level electron. It's 3s1. So I have one valence electron. I'm going to do that by using red in this case, and use sodium. I'm going to make a big, well, I was going to use red. Tell you what I'm going to do, because red is failing me. Don't have time for failure. Okay, we're going to use an X, just to kind of symbolize that this is the sodium electron, okay? Chlorine. Lewis structure for chlorine. It's a column 7 element, has 7 valence electrons. Whatever energy level it is, if it has 7, I know that it's got 2s and 5 p's. It happens to be in the 3rd energy level, so it's 3s2, 3p5. So for a total of 7, because the column 7 has a total of 7 valence electrons. I'm going to use the dots for that. 7, I know that I'm going to go around almost 2 times, right? 1 shy of 2. So I'm going to center my dots just to make it easier, make them supersized here. Okay. Is everybody comfortable with those 2 Lewis structures? All right. So what happens? Mr. Sodium and Miss Chlorine, okay? They happen to be at the same place, you know, under the sea ball, whatever. Movie reference there, if you've, okay? So they're at the same place, same time, and This guy's over here saying, man, I just want to get rid of this electron. I'm sick of this. I'm holding on to this one. You know, it's like having a pocket full of bills and then having that quarter and saying, the quarter, let me just get rid of this so I can just, okay, I got one extra here. I want to get rid of this one. If sodium gets rid of this one electron, what is its valence going to look like? Its valence level, electrons. If sodium gets rid of this one, it's now going to have the same electron configuration as neon, right? Man, I wish I could be like neon. Neon's got like the perfect setup. For me to be like neon, I need to get rid of this stinking one single valence electron so I can, if I get rid of this one, then I'm back to full orbitals. None of these partial orbitals to try to manage. Okay. Chlorine. I just need one more quarter and I could make a perfect bill. I got 3 quarters. If I just had one more quarter, I could take it to the table, change it in for a dollar bill, be perfectly set. That's the way I want it to be. Chlorine, Miss Chlorine's looking for an electron. Mr. Sodium's trying to get rid of electron. Guess what? Same place, same time, they strike a deal. Tell you what, you want this electron? I love that. You can have it. Just take it. Sodium gives up its electron to chlorine. Okay? Now, we leave sodium looking like this, but technically, sodium now has 8 in its valence, right? It got rid of the 1, its first third energy level electron. It gets rid of that. Now it has a perfect octet. We're not going to draw 8, but just know that it lost that 1 hanger on. Now it has 8. Chlorine had 7, but it took what sodium gave, and now chlorine has 8. So in terms of octet rule, do you see that both of those atoms now have satisfied the octet rule? They both have 8 valence electrons. Okay. This is why sodium and chlorine can't combine in any different way than 1 to 1. Because once this chlorine picks up that 1 electron, it doesn't want any more electrons. It's not looking for another sodium to help complete it. Okay, it's done. This sodium is done. This chlorine is done. All things equal, the reaction engine stops. Boom. Because all the chlorines and all the sodiums are satisfied. But something happens. What was the charge of sodium before it gave up an electron? Electrical charge. What was the net electrical charge of sodium before it gave up the electron? Its net charge was neutral. Nothing. How many protons did it have? How many protons did sodium have? 11. How many electrons did sodium have? 11. I've got 11 positives and 11 negatives. What's its net charge? Neutral. It has no charge. Every positive has a negative. They balance each other out. No charge net. Now, sodium has given up an electron. It has 1 less negative than it had before. How many protons does this sodium atom have now? How many protons? Has to have 11 or it's not sodium, right? It still has 11. You're not messing with protons. So this has 11 protons. How many electrons does it have? 10. It used to have 11, but it gave up 1, right? So now it has 11 positive charges and 10 negative charges. What is its net charge? Plus 1. It has 11 positives, 10 negatives for a net charge of 1 positive. Okay? Be comfortable with that. It had 11 positives and 11 negatives. It gave up a negative. Because it gave up a negative, it is now 1 positive. 11 protons and 10 electrons. Now, chlorine. How many protons did chlorine have, or does it still have? Because we don't mess with the protons. How many protons does chlorine have? So 17 protons. How many electrons did chlorine have before it took another one? 17. But now it's taken another one, so it has a 18, right? So it has a net charge of 1 negative. So we have to write up here that it has a negative charge. Now let me ask you this. If I had two nondescript balls over here, like beach balls or something like that, and I told you that one of those had a negative charge and one of those had a positive charge, and I said, how were they going to influence each other? You have enough chemistry now to say, hey, Mr. Baker, I know that if I bring a negative charged object and a positive charged object next to each other, they are going to attract, like two magnets. Boom, they're going to come together. What do you think, junior scientists, happens when a positively charged sodium ion, because it's lost an electron, it's a positively charged ion known as a cation. It's a specific name given to metals who give up electrons become positive. It's a cation. This cation is in proximity to this anion, the negatively charged ion, anion and cation. When they're in proximity to each other, all they see is, hey, look over there. There's somebody who's positively charged. Hey, look over there. There's somebody that's negatively charged. What happens to them? They come together. They come together and form a Lewis structure that looks like this. If you can imagine in your mind's eye that here is the outer limits of what we know as the sodium ion, the sodium ion, and here is the outer limits of what we know as the chlorine ion, and they are stuck together by the electromagnetic attraction of their charges. A positive sodium ion, a sodium cation, is attracted to a negatively charged chlorine ion, an anion, and as a result of their opposite charges, they get attracted and get stuck together like magnets. If this is a +1 charge, and this is a -1 charge, so they attract each other and get stuck together, what is now the charge of the whole molecule? This side is positive, this side is negative, one positive and one negative, and when they come together, positive and a negative, what is their net charge? Neutral. So now that they have electromagnetically come together and are attracted to one another, now any other ion going by kind of doesn't see them anymore. Why? Because they have no charge. Cations are going by, other sodiums, not interested. There's no charge there. There's no electrons available. Nothing's going on there. I'm going to go searching for another. Oh, there's a chlorine anion over there. Let me go over there. Boom, form a pair. This is why sodium and chlorine can only bond in a 1-to-1 relationship. Because once this happens, once the electron goes over there, once they have their opposite charges, boom, they come together. Now they have no charge. They're not attracting anybody else. They are mutually satisfied in this relationship. Okay? So sodium gives up an electron. Chlorine willingly receives the electron to complete their octets. That simultaneously gives them net charges, which causes them to attract, and together they have a neutral charge for sodium chloride. Let's go through the book on 136 and 37, make sure I've covered all the stuff in blue, all the important notes. Top of page 137. In ionic compounds, the nonmetals try to gain electrons. That's what chlorine did, right? Tries to gain. So their Lewis structures reach the ideal configuration of 8 dots. The exception may be helium, right? It already has 2. It's a noble gas. Further down the page, in ionic compounds, the metals, in this case sodium, tries to lose electrons, so their Lewis structure will have 8, or the ideal configuration around them. That's why hydrogen, lithium, and beryllium are trying to lose electrons. You see on 138, as I've already described, the positive negative charges. An ion is an atom that has gained or lost electrons, becoming electrically charged. We covered that last module. When you've got more or less electrons than you have protons, then that atom has a net charge. And when it has a net charge, it's ready to chemically react. And that's what we're describing here, a chemical reaction. A transfer of an electron causing opposite charges, causing an attraction that results in neutralization and a structure known as a molecule. See there on the page, a cation is a positively charged ion, an anion is a negatively charged ion. Thing to note at the bottom there, this is where we get our naming paradigms for ionic and covalent. It says here at the bottom of the page, the positive cations. What do we call this? When sodium loses an electron, its name is still sodium. It's a sodium ion. Okay? Sodium, the metal, becomes known as sodium, the ion. Chlorine, the atom, becomes known as an ion. Its ion name is chloride. So a sodium ion and a chloride ion. Okay. The anions take on the "ide" name. So while this might be sodium, the atom, the neutral atom, sodium, the ion, this is chlorine, the neutral atom, chloride, the ion of chlorine. And that's why we get sodium chloride in the naming paradigm. So again, pretty straightforward. We're going to use sodium as the example, or sodium chloride as the example for ionic compounds repeatedly, because the rules that apply here apply all the time. It's the same principle. Sometimes the numbers are a little bit different. We're going to use an example now of magnesium fluoride. It's the same principle, but we're going to walk through it using different elements. Clear to erase? Good notes for potential future quizzes and tests and stuff? Okay, good. And for studying, and for homework, and for all those other good things too. All right. The book then walks us through magnesium fluoride. Let's go ahead and write, I'm going to go ahead and, like the book does, write magnesium, fluorine, magnesium, number of valence electrons, column 2 element, I'm going to have 2 of them, fluorine, oh, excuse me, I would put FL, bad, just F. I like to have two letters as well, but okay, so it's just F. It's a column 7 element, right? So I know I'm going to go around twice. What I'm going to do now, just to make it easier, and you have this liberty once you figure out how to do this, I'm going to orient my open slot over here to this side. Tell you what, I'll take that back. I'm just going to do it the way you guys would do it right now. Beginner dot, beginner dot. So beginner dots would look like this, right? I'm going to offset this because I know I'm going to put one in there in the future. But magnesium, valence 2. Fluorine, valence 7. Now the principle we just learned would be that, hey, magnesium is a metal, it's trying to get rid of electrons. Fluorine is a nonmetal, it's trying to get electrons. So when I do this, I can say, wait a minute, there's an opening right there. There's an open address, if you will, on fluorine right there in that position. I'm going to go ahead and fill that by giving it one of these electrons here. Let me give it that one. I'm going to show this as an X over here just to say where it came from. Okay, it came over here from the magnesium. Okay, do you see now that fluorine, this fluoride ion, is satisfied the octet rule? Do you see that? It has its 8. It's now this atom right here that's become this ion. It's done. It's happy. It's not looking for any more electrons. It's going to drop out of the whole reaction game now. Okay, that's great for the fluoride ion, but what's going on with magnesium? Still has one. Well, guess what? When you find one atom, you're likely to find another one. So in this big mix, we're going to say there's another fluorine over here. It is still a neutral atom. It's not become an ion yet. It has 7. This one has 7. This one now has 8. This one still has 1 to give, and this one still wants 1. Strike a deal. Boom. There we go. So magnesium has given up 2 electrons, 1 to this fluorine and 1 to this fluorine. So this has become a magnesium cation, and we have 1 fluorine anion and a second fluorine anion. These have both become what charge? The fluorines have now become, what charge does the fluorine now have? Each one of them has a charge of negative 1 each, right? This one gained an electron, so it's got a negative 1 charge. This one gained an electron, so it now has a negative 1 charge. What's the charge of my magnesium? My magnesium cation has a charge of positive 2. We're going to write it this way, 2 positive. Okay? So my fluorine has become fluoride. Each has a 1 more electron than protons, so each have a negative 1 charge. Magnesium has given up 2 electrons, so it has 2 electrons less than the number of protons, and it now has a positive 2 charge. Now, if we were to walk this thing through slowly, hopefully you would see that, hey, here's my magnesium ion. Okay? It has a 2 plus charge. This negatively charged fluoride anion is going to be attracted to the positive magnesium. Do you agree? It's going to come down, and it's going to be electromagnetically attracted to the magnesium. What about this? When these two come together, this has a plus 2 charge, this has a minus 1 charge. What's the net charge of this combination now? Plus 1. Guess what? We've got a negative 1 right here. This negative 1 is going to come down. It's attracted to this group that has a positive 1. It joins, and it brings another negative. So now what is the net charge of these 3 things stuck together? It's neutral. Okay? So they're attracted to each other because of opposite charges. But once they connect, they neutralize each other for the net charge of the whole, while still being attracted to each other because internally they still have opposite charges. This is still carrying a positive 2 charge, and it's neutralized by this negative 1 charge and this negative 1 charge to have a net charge when they're together of neutral. If you were to break them up, they would take on their individual charges again. They're only neutral because they're together, and they're only together because they're oppositely charged. Okay? This is why magnesium and fluorine only combine in this relationship. What is the formula for magnesium fluoride? Look right here. How do I form one of these molecules? What do I need? What are the building blocks that make this up? Is there carbon in there? Is there lithium in there? Is there magnesium in there? Oh, magnesium's in there. I need magnesium. Is there chlorine in there? You guys are not very awake, so I'm just giving you lots of options. So is there rubidium in there? Is there oh yeah, there's fluorine in there, right? Okay, so I need magnesium and fluorine. That's what I need to make this thing up, right? I'm not an alchemist. I'm not going to make gold out of combining different chemicals together and mixing it up with, straw and a little bit of duck waste. No, I'm making this out of magnesium and fluorine. Magnesium and fluorine. Hey, which is the metal? Magnesium or fluorine? Magnesium. So I'm going to start my chemical formula with the metal, magnesium. What else is in there? There's fluorine. So I'm going to go ahead, magnesium fluoride, because it's ion now, it's magnesium fluoride. Oh, how many magnesiums do I need? 1. How many fluoride ions do I need? 2. Can I add another magnesium to this molecule? It's neutrally charged, right? Even if I had another magnesium that had a positive charge out here floating around, it's not going to be attracted to this. This is neutral. Nobody here wants their electron. Nobody here is electrically charged to draw them in. Once this happens, it's done. That's why ionic compounds only form in a very specific one relationship, element to element combination. We don't call this magnesium difluoride because there's no such thing as a magnesium trifluoride or a magnesium monofluoride. There's no such thing, which is why we can just call it magnesium fluoride. Why? Because if it's magnesium and fluorine, it's going to react like this ionically. This is the only combination that you can have. All right? It's the only combination that you can have. Now, there's a shortcut to doing this, of figuring out what is going to be the molecular formula when I have the two elements under consideration. In this case, magnesium and fluorine. If I were to come over here and say, I know that my formula for magnesium fluoride has to include magnesium and fluorine. Just bump them. Okay, good. Welcome back, Seth. Here we go. So we know that it's magnesium and fluorine. We know that these are the two. We just don't know what is the molecular formula going to be. We could sit here and do all of this and say, okay, this is going to give up one, that's going to be this positive and negative are going to interact, and I got another one, I give this one away, it becomes positive, and it's going to come down here and combine three and neutralize. Okay, good, we're done. Or we can come over here and say magnesium and fluorine. Okay, magnesium. What charge does magnesium want to have? Magnesium want to have. So I come over here, I find magnesium on the periodic table. Magnesium's right over here. And I say, okay, magnesium wants to have a positive 2 charge. How do I know it's positive? It wants to be positive because it's a metal. It wants to be positive 2. Why? Because it's in the second column, it needs to get rid of 2. If it were able to get rid of 2, it would have a +2 charge. You see that? Magnesium wants, again, personification. Magnesium doesn't really care, but for us to understand it, magnesium wants to get rid of 2. It wants to have a 2 positive charge. This is what it wants to have. 2 positive. Okay. Fluoride. Well, fluorine is a column 7 element. Fluorine, because it's a non-metal, wants to get electrons. So it wants to have a negative charge. How many does it want to get? 1. So it wants to have a 1 negative charge. So hopefully now you've written down the different elements. Written down the different elements and say, what charge does it want to take on? Just figure out what charge does it want to take on. And then, it's real simple after this. Wait just a moment. So magnesium wants to go to 2 positive. Fluorine wants to become fluoride with a 1 negative. What I'm going to do is I'm going to disregard the signs, because hopefully you see, hey, it's positive and negative. They're going to balance each other out. So I'm no longer going to consider what the signs are, and then I'm going to transpose as subscripts. I'm going to take the charge from the one and bring it down and make it the subscript of the other, which becomes Mg. The subscript for magnesium would be 1, however, we don't write 1s, because if it's a 0, it wouldn't be there. If it's a 1, it shows up. If it's 2 or more, we write it down. So Mg should be 1, but that's implied. Fluoride, fluorine, subscript 2. Fluorine has a subscript 2 because magnesium wants to have a positive 2 charge. Magnesium has a subscript of 1 implied because fluorine wants to have a 1 negative charge. You can do all of this logic, or you can write down here and take the charge coefficients and bring them down as subscripts for each element. So MgF2 is the formula for magnesium fluoride. Magnesium gives up 2 electrons one electron to each of two fluorine ions to make them fluoride ions. They then come together, and the +2 for magnesium balances out the two -1s from the two fluorines to form a neutral molecule. That is ionic molecules and ionic bonding. It's the principle behind it. So everything we do now, moving forward, we're combining a metal and a nonmetal. The reason those elements become ions and then become attracted to each other and form molecules is based upon this principle right here. Completing the octet rule, taking on charges, and then being attracted to one another. If you notice at the bottom of page 140, they give you a basic table of the different ions that are available or different ions that will be created. And then on the next page, they give you a series of rules. But one of the things is you don't have to technically memorize all these rules. We're not going to give you the exceptions. Now, read through that on your own study. But they go through and tell you, hey, this atom, for example, is one of the exceptions. We'll discuss that later. And this atom is an exception, and we may discuss that later. But until we discuss them later, what you actually just need to know is what we've talked about here in terms of if it's a metal, it wants to give away electrons and become positive. If it's a nonmetal, it wants to receive electrons and become negative. How many? Based upon the column it's in, of a metal trying to get rid of 1 or 2 or possibly 3, and nonmetals wanting to receive 1 or 2 or 3. Again, based upon the column it's in. Column 5 elements want to receive 3 to make 8. Column 6 elements want to receive 2 to make 8. Column 7 elements want to receive 1 to make 8. Column 8 elements want to be left alone. They're not interested. They're not going to play this game. They've already got all they want. They want people just to leave them alone. That's why it takes a lot of energy to get them to do things, because you've got to bring energy into it. Naturally, the reaction energy is not there to make it happen. That's why they're inert. That's why they're noble gases. That's why they're baseline for a lot of different things. For fun, let's go ahead and look over on example 4.2. What is the chemical formula for the ionic compound formed by aluminum and sulfur? And what is its name? Aluminum and sulfur. When I say I've got aluminum and sulfur, first thing you're going to do is try to figure out, is it a ionic or covalent bond, right? Ionic or covalent molecule. I've got aluminum and sulfur. Aluminum is a metal or nonmetal? It's a metal. Sulfur is nonmetal. I've got a metal and nonmetal. It's going to form an ionic bond, right? So we've got aluminum and sulfur. Question for you. What is aluminum, what charge does aluminum want to have? What does it want to have? +3, good. It's a metal. It wants to lose electrons and become positive. How many? It's column 3. It wants to get rid of 3 electrons. By getting rid of 3 electrons, it's going to assume or become a +3 cation. Sulfur wants to become sulfide. Sulfur is a column 6 element. Column 6 wants, it's a nonmetal that wants to receive electrons and become negative. How many does it want to receive? 2, right? It's at 6. It wants to get to 8. It needs 2. Everybody follow that? Sulfur wants to become sulfide. Sulfide has a -2 charge. Aluminum sulfide, what's the chemical formula for aluminum sulfide? I drop the charges, transpose the coefficients for Al2S3. Think of it this way. This says I have 2 aluminums, right? If I have 2 aluminums and each one of them has a 3 positive charge, how many positive charges do I have altogether? 2 sets of 3 for 6 positive charges. Do you see that? If these 3 positive, if I have two ions and each one is 3 positive, I've got a total of 6 positives, right? And then I have 3 sulfurs, those sulfides. 3 sulfides, each sulfide has 2 negative. So if I have 3 at 2 negative each, how many do I have? 6 negative. Guess what? 6 positive neutralizes 6 negative, and it's a neutral ion, or neutral molecule now. So I'm driving to neutralize the charges. We drive to neutralize the charges, and the way we do that with the shorthand is to ignore the charges, bring the charge coefficients down as subscripts, and form the molecule. These 2 aluminum ions, cations, give me +6 charge. These 3 sulfide ions give me -6 charge. They balance each other out for a net neutral charge. And that is the only way that aluminum and sulfur can combine ionically, is in a 2 to 3 combination. You're not going to have aluminum 3, sulfur 3. You're not going to have aluminum 2, sulfur 4. It's not going to happen. Why? Because when they exchange electrons, take charges, and then get attracted to one another, they're full. They're satisfied. There's no other way that no other ratio for these building blocks to build that molecule. Next one, barium oxide. Well, barium is a column 2 element. So what does its ion charge want to be? Lose makes it +2. +2. Oxygen is a column 6 element. It wants to get to -2, right? It has 6, it wants 8. So barium wants to be a -2, oxygen wants, reverse. Barium wants to be +2, oxygen wants to be -2. Guess what? It ends up being a 1-to-1 relationship. It's going to look like this. If we went with barium 2, oxygen 2, because they're the same charge level, 2 and 2, we could write it as 2 and 2, but that simplifies down to 1-to-1. So that's one little trick you need to know, is if they're the same numbers, if they're related to one another, you get to the lowest common factor. In this case, it would be 2, so it becomes barium oxide. Hopefully you see that a +2 and a -2, I just need one of each and they neutralize. Right? 1, 2 positive, 1, 2 negative, boom, they're together, neutral. No more. It's barium oxide, just like that. And last one, sodium nitride. Sodium wants to have a, what charge? Wants to go to +1. Nitrogen, over here is a column 5 element. It wants to go to 3 negative, okay? So the chemical formula is Na3N. We don't write the 1. When sodium is +1 and I have 3 of them, I have a total of 3 positive charge. Nitrogen itself has a 3 negative charge, and the 3 positives cancel the 3 negatives for neutral atom of Na3N. Sodium nitride. Yes? Nitrogen goes to -3 because it starts at column 5. It has 5 electrons in its valence shell. It has 5. It wants 3 more to get to 8, right? So it has 5. If it takes 3 more, it gets to 8. So ideally, it wants to be 3 negative. If we give it a way to do that by putting it near sodiums, the sodiums will give it, because they're trying to get rid. Hey, please take these electrons. Nitrogen comes up, says, I need 3. The first 3 sodiums to show up say, there you go, boom, boom, boom. Those 3 sodiums are done. They don't have any more to give. Nitrogen's done. It can't take any more. But because they gave and received, now they're oppositely charged, and they get stuck together because of their charges. But they can only go 3-to-1. Because if we had added another nitrogen, we would have to add 3 more sodiums to balance it off. So it's always going to be a 3-to-1 relationship.